A lot of results in combinatorics involve permutations of 1 through n which avoid certain patterns. So let's talk about what that means and then give an example of a result which involves pattern avoidance and Catalan numbers. So let's let Sn be the symmetric group. That is permutations of 1 through n. And for W, which I'll write as W1 through Wn in the symmetric group, call Wi1 through Wik a subword if I1 through Ik are an increasing sequence of indices. And a contiguous subword if I1 through Ik equals I1, I1 plus 1, I1 plus 2, etc. up to I1 plus k minus 1. That is if these k indices are all next to each other. So for example, for W equals 2, 3, 1, 5, 4, 6, 2, 1, 4 is a subword. Because we've got 2 before 1 before 4. And 3, 1, 5 is a contiguous subword. Because not only do we have 3 before 1 before 5, but they're all right next to each other. Now given, let's say, B1 through BK, or permutation of k letters, we say that a subword Wi1 through Wik of W matches the pattern B, B1 through BK, if Wi1 through Wik, the letters, appear in the same relative order as 1 through k do in as B1 through BK do in B. So the subword WI1 through WIK matches the pattern B1 through BK if the letters appear in the same relative order. That is, jth lowest letter of WI1 through WIK is in position J. Is in the same position that contains J and B. I'm going to do an example of that because it's easier to do an example than to explain it. So let's look at subwords of 2, 3, 1, 5, 4, 6. Matching the pattern one, two, three. So we're just looking for increasing three-letter subwords. So I see 2, 3, 5, 2, 3, 4, 2, 3, 6, 2, 1 wouldn't work because 2 is bigger than 1. 2, 5, 2, oh, yeah, wait, 2, 2, 3, 5, 2, 3, 4, 2, 3, 6, 2, 5, 6, 2, 4, 6. That's it starting with 2. Then 3, 5, 6 would work. 3, 4, 6. And that's it starting with 3. And then 1, 4, 6. So all of those are subwords matching the pattern 1, 2, 3. Because they're subwords where we've got smallest letter, second smallest letter, third smallest letter. Just to do another example, let's look at subwords matching the pattern 2, 1, 3. So we need second smallest letter, largest letter among the three. So 2, 1, 5 would do it. 2, 1, 5, 2, 1, 4, 2, 1, 6. I guess that's it that starts with 2 because the second letter would have to be 1. And for 3, the second letter would have to be 1 also. So 3, 1, 5, 3, 1, 4, 3, 1, 6. There couldn't be any starting with 1 because 1 is the smallest letter. Then 5, 4, 6. 5, 4, 6 matches that pattern because we have second smallest, smallest, largest. 5, 4, 6. Then we call W B avoiding if no subword of W matches the pattern B. So for example, 2, 3, 1, 5, 4, 6 is, I think it's 3, 2, 1 avoiding, because we never have large letter followed by smaller letter followed by smaller letter. There's no decreasing sequence of 3 letters. Now I wrote down that it is also 3, 1, 2 avoiding. So we can't have a big letter followed by 2 increasing letters which are smaller than it. So it certainly can't start with 2 because it would need 2 smaller letters after that. Can't start with 3 because it would need 2 smaller letters after that. Certainly can't start with 1. 5, 4, 6 is not of that pattern because 6 is the greatest of these 3. So it's also 3, 1, 2 avoiding. For some patterns, there is a nice formula for the number of B avoiding permutations in Sn. For example, the number of 1, 3, 2 avoiding permutations in Sn is 1 over n plus 1, 2n choose n. Now we can show that by defining a bijection to something else that we know, which is counted by Catalan numbers, but we need a couple of definitions and lemmas first. So given a permutation, define the code, so let's call this W. W equals W1 through Wn. The code of W is the word C1 through Cn. Where Ci is the number of letters to the right of Wi and smaller. So let's quickly write out all the codes of permutations in S3. So we have 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. The code here is 0, 0, 0 because there's nothing to the right of 1 and smaller than it, nothing to the right of 2 and smaller than it, and nothing to the right of 3 and smaller than it. Here we have 0, 1, 0 because there's one letter to the right of 3 and smaller. Here we have 1, 0, 0. And by the way, that last digit of the code is always 0 because there's never anything to the right of the rightmost letter and smaller than it because there's nothing to the right. So we have 1, 1, 0 because these are both greater than 1. 3 is bigger than 1 and 2, so that's a 2. 1 is bigger than nothing. The last letter is bigger than nothing. And here 3 is bigger than two things to its right. 2 is bigger than one thing to its right, and 1 is bigger than 0 things to its right. So those are the 6 codes of the 6 permutations in S3. So the least that a digit in the code can be is 0. They're all greater than or equal to 0. The most it can be, so if we're in the I position, I guess there's n minus I letters left. So it could be greater than all n minus I of those. So every letter in the code, the letter in position I is somewhere between 0 and n minus I. Now let me write some histograms next to these codes, just to graph these numbers. So 0, 0, 0, by histogram I mean K blocks where we see a K. So 0, 1, 0, 1, 0, 0, 1, 1, 0. Two, 0, 0, and 2, 1, 0. Now if we follow the histogram along from left to right, we see that in 5 cases we have a histogram where the top borderline goes to the right and down only, never goes up. But here for 1, 3, 2 we go up before we go down again. Now the third Catalan number is 5, so we might guess that permutations avoiding 1, 3, 2 are counted by Catalan numbers because we can see the lattice path there basically. It's going from upper left to lower right rather than lower left to upper right, but it's the same thing turned around. Alright, now I want to claim that the number of weakly decreasing code words of permutations in Sn is a Catalan number. Well, we proved something like this in discussion the other day. We had sequences of letters so sequences of n letters where each letter was at least 1, and then the ith letter was no greater than I. The number of sequences A1 through AN with AI somewhere between 1 and I is the Catalan number, 1 over n plus 1, 2n, choose n, by discussion. Now if we subtract 1 from each of these letters, then we'll have something that's between 0 and I minus 1. So we'll subtract 1 from each letter. And reverse the sequence. So we'll have an minus 1, an minus 1 minus 1, an minus 2 minus 1, etc. over to a 1 minus 1. And now instead of being greater than or equal to 1, since we subtracted 1, each of these is greater than or equal to 0. And if an is less than or equal to I, then we've got this one is less than or equal to I minus 1, and this one is this is n minus 1. This one is less than or equal to n minus 1 minus 1, n minus 2. This is less than or equal to n minus 2 minus 1, n minus 3, etc. And that one is less than or equal to 0. Which is exactly what the code words of permutations are. And maybe it's worth stating that all sequences A1 through, maybe I should say C1 through Cn, with Ci between 0 and n minus I are codes of permutations in Sn. Alright, now I claim that a permutation avoids the pattern 1, 3, 2 if and only if its code is weakly decreasing. So to start the proof, let's suppose that the code is not weakly decreasing. So that means that we have Ci less than Ci plus 1 for some I. That means that there's something to the right of Wi plus 1 let's say Wk. So we have Wi plus 1, and then later Wk. So there's some letter Wk that's less than Wi plus 1, but not less than Wi. Because the number of things to the right of here is greater than the number of things to the right of here that are less than this and less than that. So there's some letter to the right of Wi plus 1 that's less than Wi plus 1 and not less than Wi. So Wi plus 1 is greater than Wk. Wi is less than Wk. But if that's the case, then Wi is the smallest, and Wk is the second smallest, and Wi plus 1 is the third smallest. So these three letters match the pattern 1, 3, 2. All right, now let's, for the other direction, I guess I'll leave the claim here and I'll just start again up there. Let's suppose W has at least one subword matching the pattern 132. So let's choose one. WI1, WI2, WI3, which minimizes I2 minus I1. So we'll make these letters be as close as possible. And if we do that, then there's not going to be any smaller letter between WI1 and WI2. So this will be the right nose small letter before WI2. So if we have WI1 here, WI2 here, there's no letter in there is smaller than WI1. Now let's so there's no letter that's smaller than WI1 in here. So if we take the code and look at letters that are smaller than WI1 and after it, they would all have to be after WI2. So let's let D1 be positions after I2 holding letters smaller than WI1. And let's let D2 be positions after I2 holding letters smaller than WI2. Now D1 has to be a proper subset of D2. Because all of the letters which are smaller than WI1 have to be also smaller than WI2, the greater letter. So that's why it's a subset. It's proper because WI3 belongs to D2 and not to D1. Now the code letter so CI2 is the cardinality of D2 and CI1 is the cardinality of D1. So that means that CI1 is less than CI2 and the code is not weakly decreasing. Alright, I've erased the claim, but we just proved that W avoids the pattern 132 if and only if its code is weakly decreasing. Let me write down the two claims we just proved.